Boom. No, it's working. Good. Okay. So, I was taught C++ is a multi-paradigm language. So it supports a lot of paradigms like object-oriented programming or procedural programming, a lot of things like functional programming. Okay, so C++ is really a functional programming language. Do you think C++ supports functional programming? Well, that's a good question. I wanted to try it out. So I know a bit of Haskell, and I know that Haskell supports a lot of interesting things like lazy evaluation, infinite data, or for example, you can use a variable, well, actually Haskell isn't a variable, but something like that. So you can use the data to define itself. So you can use, so you can do a lot of things which is not quite used in C++. So wanted to know if it can be done in C++. So today I will talk about how to actually embed a language which enables you to define infinite data structures using itself into C++. So let's talk about Haskell. First, I will talk about Haskell and recursion, co-induction, and these things. And then I will talk about how to embed these operators into C++. Well, there's a limited usage of these streams in C++, but actually you can solve some specific problems with it. And lastly, I will talk about how I implemented the infinite data structure in C++. So let's talk about Haskell. Haskell is a lazy functional language, and you can define new data types in Haskell, which is quite unusual in C++. So in Haskell, what you have is, well, it is called algebraic data type. It means it has two data constructors, so you can create a list. So this is a list, and you can create a list with nil or with cons. So there are two ways to create a list, using nil, which represents the empty list, and cons, which is, well, A is the element of the list, and well, this is called the tail of the list. So this is the head, and this is the tail. So you can prepend that element in front of an existing list. So that's the two data constructors we have. So, well, pretty much that's a list in Haskell. Well, actually, I think it comes from Lisp, to be precise. So you can do something similar in C++ if you know Boost variant. Boost variant enables you to define variant records, which is quite similar to algebraic data type. So, okay, how can you create a list in Haskell? You can create a list with the nil, and you can prepend 2 to nil to the empty list, and you can prepend 1 in front of the list containing only 2. Okay, well, actually this is not quite how Haskell creates it, but it's more readable. The actual Haskell syntax uses this column. So this is an empty list. You prepend 2 to the empty list and prepend 1 to the list containing 2, which is a list of 1 and 2. Okay, so that's Haskell. That's list in Haskell. Okay, well, actually, note that the associativity of the column operator. Okay, so if you want to put a parenthesis, the parenthesis is around 2 and the empty list. Okay, so it's right associative operator. Okay, we need two functions, which is quite fundamental in in functional languages. One is map, and the other one is civil. Map actually takes a function and a list and apply the function to all the elements of the list. So if you, this is a successor function, so you can take the successor of all the elements of the list, which is successor 1, successor 2, so it's 2 and 3. Or you can combine two lists with a binary operator like a plus. So this is the plus function, and you can combine the two lists element-wise, so adding 1 and 2, so that will be the, oh. Yeah, I think that's a typo there. So adding 1 and 2 and adding 3 and 3. Which, okay, so I think I should change this to asterisk. Okay, fine. Okay, so co-induction. Yeah, co-induction is a great word. I'm not sure I completely understand it. It means you can use data to, so, well, actually you can break down the data to simpler data, and that's how you can define something that is that what is called co-induction. Basically means you can use itself to define so-called code data. I will talk about code data. And well, what I'm doing here, and the examples are from somebody who called Ralph Hintze from Oxford. And well, actually this is his paper, and I read that, and I wanted to implement it in C++ because this paper is about Haskell. So what actually I did is this, I implemented this paper in C++. Okay. So what is a co-induction? How can we define data with co-induction? So for example, X is a data, and we can define X by prepending 1 to X. So if you substitute X to its own definition, you will get 1 and X. And if you do this, well, infinitely, then you will get an infinite list of ones. Okay, you can do this with 1 and 2. You can prepend 1 and 2 before X, and you can get a stream of alternating 1s and 0s and so on. So a bit, so it's a more interesting example. So what happens if you map X with the successor function and prepends 1 before it? Okay, so the first element will be 1. We can substitute it back, and what we'll get is something like this. Okay, so this is the first step. We substitute X into itself. And, well, the definition of map is something like apply the function to the head element and map the tail element. Okay? So actually, it's defined by recursion. Okay, so we use the definition of map, and now it's actually 0, 1, and there are 2 successors, so it's 2. So so actually it's an increasing sequence of sequence of increasing numbers. Okay, so this is co-induction. And what is co-data? Well, co-data is actually something like a data. Okay, so list has a nil constructor, so you can create a list just like well, say nil. This is an empty list. If you leave this out, it's well, it's a more interesting problem how to define. This is called stream. So stream means prepending an element before a stream, pretty much like a list. But stream doesn't have an empty stream constructor. So how can you create a stream? There is only one way to create a stream, using co-induction. So using another stream or itself to define it. Okay. So you can do the same in C++. So for example, it's pretty much the same as this data. It's well, it's a stream of type T, or element, something like that. So there is a element here, and there is a reference to another code data here. Oh, a reference. So that's the trick here. If we use a reference here, we have to initialize it. We have to give some value to it. Okay, so when we try to create our first instance of this type, which is S here, we have to put something to this field. And we only have one, it serves. So we have to put it serves. And this will be an infinite, so this stream will represent an infinite number of zeros. So actually this thing exists in C++ and you can do it in C++, but well, it's not quite convenient how to create. So not quite clear how to create C-bit and well, such structures in C++. So the next question is, how can it be done in C++? Okay, to do this, I defined a type stream, which is a template parameter, and I define this operator. Well, so the colon operator has an associativity and a precedence in Haskell, and I wanted to find an operator in C++ which has similar properties. So I choose this one, and well, it looks good. So I really like this operator. It's something like, so it's prepending 0 before S. Okay, so this is a constructor for a stream, and so this is actually the same in C++, same as this Haskell code here. Okay, so we can do this. Well, actually, you can use S to define itself. It will cause some problems, but you can do it. Okay, and you can create a map function. It's pretty convenient. You can create a map function which takes a function which is some binding 1 to the second parameter of the plus operator. So it's using some functional header. Using the functional header is pretty easy to do. Okay. So, an example. Of course, the first thing I did was to write plus operator for streams, so you can add 2 streams element-wise. So, well, actually, it's the same as cwidth, and it's std plus something. Okay. So you can define a string with this expression. Okay, what is this expression? So the first element is 0. You can see this. So before evaluating everything, we know that this is 0 here because we prepend 0 before this fib data, and this is 1. And we add these 2 streams. So we add this one const fib, and I will call this operator const here. Okay, I don't know what is its name, but const is something I use. So I think that's a good name. Okay, so we add these 2 strings, so these are the addition. So this is 0. Okay, so the first element of fib is 0. Good. So we can back substitute it. Now we know the second element, which is 1. Back substitute, and so on. So do you know what's this? 0, 1, 1, 2, 3, 5, 8, 13. Yeah, it's the Fibonacci sequence. So this is the co-inductive definition of the Fibonacci sequence in C++. Okay. Do you think it's useful? Well, there is a limited usage when you can use co-induction, for example, in dynamic programming. So if you want to solve something like the money change problem or something, then you can use co-induction. So I will show you how to solve the money change problem with this. So this stream represents how many ways are there to change $5 with using only $1 notes. So you can give back $1, then you can trace it back to how can you change $4 with only one coin. Okay, so there is only one way to do that because there is only one path to 0. Okay, so this node means that you have $5. If you give back 1, then you have to give back $4. Okay, and well, actually there is only one way, so you can define a stream which holds an infinite number of ones, and that's the solution for the problem if you have only $1 notes. Okay. Okay, it's a bit more difficult. If you want to, if you want to use $2 notes as well, then you can change $5 or you can give back $5 by using only $1 notes, or give back one $2 note and then a lot of $1 notes, or give back two $2 notes and a $1 note. So the number of paths to 0 actually solves the problem. And the number of paths can be counted like this. So actually this prepending 2 zeros before the stream itself, meaning this arrow, because you use this value here. You can do the same with recursion, just well, it will be exponential. So if you use recursion to solve this problem, so this can be, if you use recursion, these arrows will be function calls. So if you want to compute how many ways are there to change $5 with using $1 and $2 notes, then this is the function, and it will use recursion and calls this calls the function with this parameter and this, and as the two values. So that's how recursion, that's how you can solve it recursively. Okay, and so this stream actually, so the first element of the stream tells you how many ways are there to change, well actually $0. The second element tells you how many ways there are to change to $1 and $2 and so on. So actually this stream represents the solutions for the problem. And in C++, this is the solution for the problem if you had $1, $2, $5, $10, $20, and $50. This times function puts this value before, prepends this value 2 times before the change to, or 5 times before change 5, and so on. Okay, so actually you can use this, and if you use change 50 and 50, it will tell you that, I don't know, for example, the 101st element of this sequence will tell you how many ways are there to give back $100 using 50, 20, 10, 5, 2, and $1 notes. Okay, so how can you implement infinite data in C++? Well, if you have infinite number of memories, pretty easy, just you have to wait infinite number of time to fill it, but I had a better idea. Actually, it's exactly the way how Haskell works, or not exactly, but quite similar to the way how Haskell and functional languages work. So the first, so this is the Fibonacci expression, and well, this graph represents, so it's something like the abstract syntax tree of the fib of this expression. But because the expression uses itself, it's actually not a tree, but a graph. Okay, so it's not, there is nothing special with it because we used the data itself to define itself. Then we don't have a tree, we have a graph. Okay, so that's all. This green arrow is an iterator. So we have this graph, and we need an iterator to go through the elements of the stream. So when you call begin on the stream, you will get back this iterator, which points to this structure. Okay, good, because we know the value. So if you difference the iterator, it will give back 0 because the first element is 0. Okay, for plus plus, so increment the iterator. If we point to this, good. But now we have a problem. If we try to dereference this, we cannot do that because well, it's actually not a value. It's well, it's actually a rule how to calculate the value. So we have to do something with it. Okay, so that will be the result. The idea is you know the value because the left-hand side of the plus operator is actually 1. So that's the head of the list on the left-hand side of plus, and on the right-hand side is 0. Okay, so 1 plus 0 is 1. And the tail of the list on the left-hand side of the plus is this. On the right-hand side is this. Well, actually not itself, but the node it will put there. So put another const operator here and create in the tail, so in the right-hand side of the const operator, create a new plus which maps, well, which points to the tail of its arguments. So something like this. Okay. So there, here were the plus operator. There was 0 and 1. We substituted 1, and the left-hand side went here, and the right-hand side went here, and we can do it again and again and again, and we will get the Fibonacci sequence. So actually, one thing is that this stream memorizes its evaluation. So if you evaluated it once, it will remember the data, which eats up a lot of memory, of course. And well, it's not quite easy to do anything with it, so you cannot, well, at least I wasn't able to create a garbage collector for that. But, well, if you need it, you can do that, I think. Okay. So, the other problem was, so well, actually it's not really a big problem if you know how functional languages work and how lazy languages work. You know how to evaluate such a language. There is a slightly bigger problem, which is actually C++ related, is that how can you deal with uninitialized data? Because you have uninitialized data here. So how this expression works? The first thing, you declare S, or define it, declare and define it. So it's actually it has a memory to be placed. So S is actually a defined variable. But here, when you pass S to the function, the const function, const operator, then it's not yet initialized. So it's a memory garbage. You cannot touch it. You cannot do anything with it. If you try to use, or if you if you can try to do anything with it, it will be undefined. So what we can do is we can store reference to it, but nothing more. Okay. So the return value of this function is a temporary. We have to copy it. We cannot store reference. Okay. And I think there is no move constructor code here, but this is how we initialize S. So after we created this data structure, with this data structure we initialize S. Okay. So the problem is here, this expression, the return value of the cons operator must be copied, but the value or the argument must be stored by reference, and we shouldn't copy it because it's uninitialized. Okay. So luckily, when I started to implement it, well, I think there were no C++ 11 standard yet, but it was close, and that was the time when I first read about cal and R value references. So what we can do is that this is an R value and this is an R value. So what we can do is actually create a data structure which forwards this to this S value. So actually it's a template, and it depends on depends on what kind of reference is the parameter. So that's one trick, and the other trick is we need well, it's a really short meta function which calculates the storage type of the variable. So if it is a left value, then it must be a reference. Okay, so if st is a reference, then it must be a reference, because if it's a reference, that means that it might be uninitialized. So we must store a reference to it. But if it's an R value, then we must store it. So actually this is the meta function which creates this, and that's all. That's how you can deal with uninitialized data in C++. Okay. So actually, I think that was the hardest part of the implementation. Actually, there were some tricks, but that's pretty much that's it. Okay, so actually what I did is I created an embedded language when you can create infinite sequence of data using Coinductive, so using itself. And to do that, I figured out a way how you can detect uninitialized data in this case, and how you can use variables to initialize themselves. Okay, something like that. So how can you deal with uninitialized data in C++? So thank you for your attention. If you have any questions, you can ask it now or grab a beer and we can talk about it, or you can download the source code from GitHub and examine it if you want, or if you want to use it. Okay, so thank you.
Okay. So I might have missed it, but how can you actually access the fifth element of the string?
Yeah. Well, yeah, it's not quite. It's not the interesting part. So that's why I haven't really talked about this. But I'm using iterators to go through these elements. So I'm talking about that. So the string type has a begin function which returns an iterator which holds a pointer to somewhere, and so well, actually there are a lot of something like so a lot of virtual methods and something.
Okay, thank you.
You said that using this requires a lot of memory. Is this big memory? Is it a runtime or compile time memory?
Runtime.
Runtime, thanks. Whenever you increment the iterator, you add a new node to this structure in the memory.
Exactly.
And there is no way to garbage collect the old elements.
Yeah, well, I worked on an implementation, different implementation, which doesn't have memoization. It's a bit better because we don't have that problem, but then you have other problems. So for example, if you want to process a stream from a file or something, then you can do it if you don't have memoization, but I haven't implemented it yet.
Thanks.
Okay, any more questions? Yeah. Same hands keep showing up.
What is the problem with the reference counting in this case? Why does it not work as a garbage collection method?
Okay, because the string itself will always have a reference to the first element. So what you can actually do is to store the original structure, and when you I don't quite know how to do that. That's a real problem. So if you have only the I don't have any idea how to do that.
Okay, thank you.
Okay, anyone else? No? Then Attila, thank you. I believe we should have pizza soon, or it might even be here. So don't leave just yet.